Welcome to the next lecture in this video lecture series on the course Operating System. And with this lecture, we begin our second module of the course, which involves topics related to synchronization. Today's lecture will be based on software-based techniques of synchronizing processes and threads. But before we go to the details of about this software-based techniques, let's try to start this lecture by asking the question, why do we need to synchronize processes and threads? Well, the answer to this question is to prevent race condition. What is race condition? It's a situation where two or more processes or threads, you can say, processes or threads try to access, or not try to, they access and they manipulate some shared data or data structure. So this is the problem that we have. For the discussion in the discussion about processes and threads so far, we know that processes and threads, they share some data or some data structure. Now, if this happens when a lot of processes or threads they share something, now it may so happen that two or more of such processes or threads, they would like to modify the data or the data structure. Now, what is the problem associated with this? The problem is the outcome would depend on the order of the access. This is the problem that we have. Okay. So if a lot of processes and threads they start accessing certain data, certain shared data, the final outcome of this accesses that will depend on the order in which the accesses went up, and that may lead to ambiguity. Let's look at a motivational example to understand this race condition. Okay. Now, let us assume that there are two processes, Pi and Pj, and these two processes are sharing some variable called count, and this has been initialized to value of 10. Now, process Pi has a certain code, and in addition to the different kinds of instructions that it needs to execute, it performs an operation on this shared variable count, which is an increment operation. Okay? And then we have other operations after incrementing the count. So this is what Pi does, right? So this is the code of Pi, and apart from other instructions that Pi executes, there is one certain instruction which involves an operation on this shared variable called count, and that involves an increment operation. Similarly, Pj also has a certain code. It executes something, and there is one instruction which involves operation on this shared variable count, and that is an decrement operator, let's say. So these are the two processes, Pi and Pj. Pi is operating on count by performing an increment operator, and Pj is another process. It also works on count and it decrements the value of count. Okay. So this is the situation that we have. Now, if we would like to execute these two processes on a single processor, okay, so if these two processors would be executing on a single processor or core, whatever you want to call it, we know that they would be operating in a time sharing way following some predefined scheduling policy. Okay. So if that is the case, then we would find something like this, that for some period of time, process I would be executing on the core or the processor, then it will be taken out and process J will be given a chance, then I will be given a chance, J, and the process, the scheduling happens in this way. So these two processes, Pi and Pj, they alternatively get a chance to be executed on the processor, and sometimes some part of Pi gets executed, then it is taken away, and then Pj gets a chance, and this way things progress. Okay. So assuming that I and J, they work according to some scheduling policy as shown here, let's try to find out what is the final value of count if this is the way in which things progress. Okay. And we'll assume something. The assumption that we'll make is we will look at some, we'll assume that each of these operations that we do on count consist of 3 sub-operations. Okay. So if you are talking about, let's say, a count operator or an increment operator on count, so that, let us assume, consists of 3 sub-operations. So in order to execute this operation count plus plus or increment operator on count, that is equivalent to executing 3 instructions, okay, or 3 sub-operations. What are they? The first is you read this value of the initial value of count into some temporary variable called, let's say, R1. Okay. Then you increment R1, and then you write the updated value of this R1 into count. This is what we do. Okay. So let's call it Ri. So Ri is some temporary variable in which, so your arithmetic operation related to the increment will be actually happening on the temporary variable called Ri. And this is what you do in case you have count plus plus. Similarly, if you are working or if you would like to perform the decrement operator on count, okay, that is again equivalent to, let's say, something like you read, and because this operation will be happening in process Pj, let us assume that Pj makes use of a temporary variable called Rj. So you read the initial value of count into this Rj variable, then you perform the arithmetic operation, that is decrement the value of Rj, and that is your updated value of Rj. So the old value of Rj gets decremented by 1, and the updated value of Rj is what you now write to count. So this is our assumption that each of these 2 operations happening in Pi and Pj actually consist of these 3 sub operations. Okay. Now let's look at a situation where Pi starts executing, and then it follows that up by execution of Pj. Okay. So in that case, remember that the initial value of count is 10, and say Pi starts executing first, Pi executes, and let's look at the situation where Pi executes this operation, that is the increment operation on count. That is equivalent to executing these 3 operations. Say Pi had executed the first operation, that is Pi had read the value of count. Okay, this is what had happened, and as we have already discussed that because these Pi and Pj are operating in a time sharing way, okay, Pi may be taken out from execution, that is you may have something called a context switch, right? So the time unit allowed for Pi expires, Pi is taken out of execution and Pj starts executing. So in that case, now Pi stops, we have a context switch, okay, and Pj starts executing. So if Pj executes, Pj again, so the first instruction of Pj should be executed now, which is the value of count read into the variable rj, okay, and then let us assume that pj could complete the next two instructions. So pj actually completed these three instructions, okay, and then there was a context switch because pj completes its three instructions. It would complete this, and then there was a context switch. That is, you again allow pi to execute, which means that pi would execute the rest of its two instructions. It left this midway, okay, so it completes the rest of the two instructions, and this is what you get. Okay, so if this is the situation that you have, what do you expect the value of count to be? Let's look at this. So when pi was executing, it read the value of count into ri. So what is the value of ri here? Ri is, count was initially 10, so ri is 10. Okay. But before you could do something with ri, there was a context switch and pj started executing. So pj started executing, and if pj executes, pj starts by reading the value of count, which is again the initial value of count, which is 10 in this case. So 10 is read onto rj, and so rj, what is the value of rj here? Rj is 10. Now rj decrements itself, so rj becomes 1 less, that is 9, and the updated value of rj, which is 9 in this case, now is written into count. So count now has been updated by, okay. But there's again a context switch, and you go back to executing pi. Pi now starts executing by executing this instruction. Okay. What is that? That is the value of ri, which was 10, that gets incremented, so ri becomes 11, and that is what is loaded onto as updated value of ri. So ri now becomes 11, and this updated value of ri is now written to count. So count here becomes 11. Okay. So if you execute the value of the processes in this order, okay, where the first instruction of pi, after executing that, there was a context switch, pj completed 3 instructions, and then the control came back to pi, pi executed the rest of the 2. So finally what we find is the value of count is determined by the final value of ri. That's what, and we found that the value of count in this case is 11. Okay. Now let's look at another situation. This time it's the other way around. That is, you started with pj, okay, and you read the value of count into rj. Then there was a context switch, and the control was transferred to pi. Pi executed, it was this, pi executed its instructions, it could complete its 3 instructions, and then the control was again changed back to pj. Okay, pj now completed its other 2 instructions. Okay, so let's see what happens in this case. So here we find, remember that the previous case the value of count was 11. Now it's like this, we started with pj, then there was a context switch, the control was transferred to pi, pi completed its 3 instructions, and then the transfer came back to pj, pj could complete the rest of the 2 instructions. In this case what happens? The initial value of count, which is 10, is read, so rj becomes 10, okay. The control transfers to, there's a context switch, control transfers to pi. When in pi, you again read the value of count, which is 10, so ri is 10, ri increments itself, ri becomes 11, and now the updated value of count is 11. You have a context switch, the control comes back to pj. pj begins by decrementing rj, which is in this case 9, and this is the value with which count gets updated. So the final value of count here is 9. Now you see the problem. Okay. So if we started off with PI and PI was interrupted in between, it could not complete the 3 instructions. So which means this instruction was interrupted in between, and then you went on to PJ completed, and you came back to PI completed the rest of the system. You found that the count value was 11. Whereas if the same thing happens with PJ being interrupted, that is this decrement operation being interrupted in between, and you allow PI to complete its instructions, and then you come back to PJ, you find that the value of count is 9. Which clearly shows that what the final outcome of count would be, count being the shared variable for both processes PI and PJ. The final value of count, it depends on the order in which you execute these processes. Okay, so it has a direct, relevance to the order or the scheduling policy that you have, the way in which these processes they get scheduled. That determines what will be the value of count. But that's not in our hands, isn't it? Because that's decided by the scheduler, that's decided by the operating system. So if a user, if the user it uses 2 processes, PI and PJ, and it allows a shared variable among them, then it's very difficult for the user to know what will be the final outcome of this shared variable count. So any decision which would be taken on the basis of this shared variable would be a false one, okay, because you don't have any idea of what that output would be. Look at this. So in case you had, so this is the 2 situations that we saw. Now in case you would allow PI to complete all its 3 instructions. Okay? So if these instructions, let's say, would be completed in this particular order, if this was the order in which these instructions would complete, which would mean that the initial value of count, which is 10, so Ri would be 10, then it would increment itself, so Ri would be 11, count now would be 11. This same value of count, which is 11, is read by Rj, so Rj would be 11, Rj would decrement itself, it would be 10, and this will be the final value of count, which is 10. And this is what you must have expected, right? So when I said that you would execute PI and PJ, I would have, what I normally would have meant is you increment first and then decrement, or you decrement and then increment. So that's what the natural intention would be, that you increment it once and then decrement so that the value of count remains same. But that's only possible if you allow PI to execute completely, that is execute all the 3 instructions, then you allow PJ to execute, or you allow PJ to execute, that is execute all the 3 instructions, then you jump to PI and PI completes all the 3 instructions. So you see, in all the 3 situations that we have seen, the conclusion is that the outcome of this whole execution of PI and PJ, it depends on the order of these 6 instructions. Okay, if you execute the first 3, then allow the next 3, you end up into the same value. If you allow the first one to execute, then complete the second, and then allow the next 2 of the first process to execute, you get value of 11. And if it's the other way around, you get the value of 9. That is what we mean by race condition. This ambiguity that is, that comes up due to the dependence on the order of execution of these processes. And that is what we don't want. That's the problem. Okay, so synchronization, actually, the motivation of applying synchronization is to prevent race condition from happening. Okay, and how do you do that? Well, as we saw here, so the whole problem was that the 2 processes, that are dealing with this, that are making use of this shared variable. The problem of race condition occurred because of the dependence on the order. We were not sure who is getting a chance to execute on this shared data. So the way to prevent that is, first, you identify the particular portion where this shared data exists. So this is the portion where we have the shared data. Either you were incrementing something on that in case you were in process PI, or you were decrementing this shared data, or the shared variable in this case. You are decrementing something to that if you were in PG. So the first thing to do is identify the portion of the code in each of those processes where you are working with this shared data. So this is the portion in PI that involves some operation on this shared variable. And same thing, this is the portion in the code PJ or process PJ that involves some operation on this shared data. So these portions of the code which involve this shared data or data structure is called critical section. So this is called the critical section. As the name implies, yes, indeed it's critical, because this is where things can go wrong. Okay, so critical section of the code is that portion which involves some shared data or data structure. Okay, so this is the portion of PI the code that involves some shared data or data structure. And if at all there is a race condition, the race condition occurs due to these. So we have to find out some way in which we will be able to prevent this race condition from happening in these portions. Okay, so synchronization is all about preventing race condition happening in these critical sections. So henceforth, we will be calling this portion which involves some shared data or data structure as the critical section of the code. So let's say there is a process PI and there is some code, and this is the critical section. Okay, because this is the portion of the code that it shares with other processes. So I have to find out a mechanism to protect this. What do I mean by this? So the basic idea of synchronization of process or thread would be that only one process would be allowed to enter this critical section at a time. So the basic idea of synchronization is number one, only one process will be allowed in the critical section. Now, if this is the portion that this process PI shares with others, PJ, PK, etc., so all of them must be having this particular section of the code. Okay, so the rule says that if you would like to prevent race condition, you have to impose a restriction where you would only allow one process to execute in the critical section. Okay, this is the first thing that you have to do, and this is known as mutual exclusion. We will call it in short MEX, the MEX condition, the mutual exclusion condition. Only one process will be allowed in the critical section at a time, which means that until that particular process has finished executing in the critical section, no other process will be allowed to enter critical section. That means even if there is a scheduling that happens and other process PJ gets a chance, but PJ would be executing, let's say this is the situation, and suppose PI is currently executing the critical section. If there is a schedule and PI is taken out of execution and PJ starts executing, PJ will also have a code, it will also have this critical section, but PJ can execute all other code except this critical section because the critical section work of PI is not yet complete. So until PI completes the work on the critical section, PJ, even if it gets chance to execute, will not be able to execute the code in the critical section. That is what is meant by mutual exclusion. Okay. So this is the first condition that we need to keep in mind. Okay. So once we have imposed this restriction that only one process would be executing in the critical section, the obvious question that comes up is, how do you decide who will enter the critical section? That is exactly what we are going to talk about in the different software and hardware-based techniques of deciding which process will be entering the critical section. Okay. The second condition that we need to keep in mind is something called the progress requirement. Okay. What is this progress requirement? That is when no process is in the critical section and some process requests to enter the critical section, it must be allowed without delay. So this is the second condition that we need to keep in mind. Okay, what is this? And this is known as the progress requirement. So let's understand this. Suppose there are a number of processes Pi to, let's say, okay, so let's say it's P1 to Pn. These are the processes that are currently executing in your system. And out of that, there are some processes which have or would be working with the critical section. They have some shared data or data structure. So let's say there's a subset which involves some Pi, Pj, and Pk. These are the three processes which involve some shared data or data structure. That is what we have defined as critical section. So they have some critical section. And these three processes would be working in the critical section. So according to the first condition, we need to ensure that only one process would be in a critical section at a particular point of time. So it can be either Pi, Pj, or Pk. Okay. Now, when some process has to be in the critical section, we have to decide which process will be there. And that will be based on the request made by these three processes. Okay. So if these are the three processes that would like to execute the critical section, and let us assume that all three would be executing in the critical section, they have to put a request. Okay. So the second condition says, if there is no process in the critical section, let's say there was no process, Pj and Pk are not in the critical section, and Pi is currently executing, and Pi wants to enter critical section, then the process should immediately be allowed to enter critical section without any delay. Okay. But it may seem to be very obvious, isn't it? Because Pj and Pk, if no other process is there except from Pi, why should Pi be delayed? It would immediately join. Yes. So the problem is, look at this situation. There are no other processes except from Pi that wants to enter critical section. But let us say there is some process PL, okay, which does not participate in this critical section access. That means PL is a process that does not want to enter critical section. Right? It does not want to enter critical section. But there is something that is happening due to which PL is preventing PI from executing in the critical section. If this is the situation, then we say that PI gets blocked due to PL. Okay, so PL is a process that blocks PI, even though PL does not want to participate in the critical section. This should not be allowed. Let's try to understand this again. So, the decision to enter critical section should be only within processes that want to enter critical section. Say for example, if PI, PJ and PK are three processes that want to enter critical section, and there are no other processes except for these three that want to critical section, then if any one of them wants to enter, the decision should only be taken among these. No other process which does not belong to this set must not dictate whether these will enter the critical section or not. Say for example, there is a process called PL which does not want to enter critical section. That is, it is not participating in the decision making, but still it is preventing the process PI from entering the critical section. So if PL blocks PI, this should not be allowed because PL is not part of the set involving access of critical section. This is what it means. So if there is no process, that is if PJ and PK were not there, because if a decision has to be taken, it has to only to be taken among the processes that want to enter critical section. It's like this, that if you would like to choose someone, okay, you have to vote. If you do not participate in the voting process, you should not dictate who will be the leader. So the person who is chosen after a voting will only be decided by the people who have voted. People who have not voted have no right to decide who will be chosen. That's exactly the same thing. If a person who is not voting is deciding who will be chosen, then that should not be allowed. That's exactly the analogy for this. So if it is PI, PJ and PK which want to execute, it should be decided only among themselves. If PJ and PK are not there and PI wants to enter critical section, it should immediately be allowed. It should not be dictated by all other processes which are not part of this decision making. So that is what we call the progressive one. Okay. The third is we have something called bounded wait, which means that if a particular process wants to enter critical section, the decision will be taken among all those who would like to enter the critical section. The first and the second condition decides that. But after a particular process has been allowed to enter critical section, it completes its task, whatever it wants to do here, and then it comes out of the critical section. But say it again wants to enter, again a decision has to be taken and it will be allowed. But that particular process keeps on repeatedly asking for entry into the critical section. It enters, does the job, comes out, again wants to enter. How many times will you allow this particular process to go on? If you allow this process to go on indefinitely, you are being unfair to other processes because they may also want to enter critical section. So if you are talking about three processes, let's say PI, PJ and PK, and if this process PI is given unfair advantage of allowing it to enter critical section, you are harming progress of PJ and PK, and this should not be allowed. So that means there should be some restriction on the number of times that a particular process can enter critical section repeatedly. And this ensures that you are being fair to all processes that want to enter critical section. So this is what we have, and this ensures no starvation, no processes should stop. There should be an upper bound to the number of processes. Upper bound on the number of times a process can enter CS. So this is the basic idea behind. So these are the three requirements that must be ensured for any synchronization technique that you come up with. It must allow only one process to enter critical section. It must not allow processes which are not part of the critical section request to dictate other processes from entering critical section. And third, a process, if it is repeatedly it wants to enter critical section, you should put an upper bound on the number of times it will be allowed to enter critical section. So these are the three requirements that we would need to ensure if we come up with any synchronization technique. And you can see while comparing different techniques, whether each one of them they maintain these three requirements. If these three are not followed in any case, then we would discard that particular idea of synchronization. Okay. So if we have we have understood how race conditions can be avoided by introducing something called synchronization. Now we will talk about what is the mechanism to implement synchronization. How do we implement that? And the way to implement is by use of something called locks. Okay. What is lock? Lock is nothing but a shared variable. We saw that in the case of the processes Pi and Pj, which were sharing or performing some operation on a shared variable called count. So let's take the same example to understand how we can implement synchronization. So we introduce another shared variable called lock, and the rule is that whichever process gets hold of this lock will be allowed to enter the critical section. So that is the rule. Okay. So that means if we have two processes Pi and Pj, both want to do something on this variable called count, one of them will be allowed to operate on count provided that they have got this lock. Okay. And how do you do that? Well, you have to perform some operation to get this lock. Let us call it a lock operation. So this is to acquire the lock. So in order to, let's say Pi and Pj, both of them would like to get this lock, because until it gets the lock, it cannot come to this instruction. It cannot execute this instruction. So whichever process would like to execute this should use this lock operation on this L, and if you are successful in executing this instruction, or if you are successful in executing this operation called acquire, you get the lock. So both of them would try to apply this lock operation in order to get the lock variable L. If this is successful, only then you can proceed with this operation. Okay. And obviously, if both processes they have this lock operation, and if this lock operation ensures mutual exclusion, when both of them try to apply this lock operation, only one of them will be successful. Because if one of them is successful, the other would be prevented from entering critical section. Because only one of them will be able to acquire the lock, this automatically will allow mutual exclusion, because only that process who has the lock will be able to enter the critical section. So you will be protecting or guarding this critical section. Okay. But once a particular process acquires a lock, it does not mean that the lock remains with it forever. Because why did it acquire the lock? Only to to guard the critical section. That is, when it is working on the critical section, the other process should not do anything on this. When this process was implementing count, the other process should not be allowed to execute on count. That's what was the idea. But once the job of PI on count is over, there is no meaning of holding this lock with itself. Why? Because the PI now doesn't want to execute on count. It has moved to other parts of the code, and that has nothing to do with PJ. So if it holds the lock, it is actually preventing PJ from progressing. So it should not allow. That means when you are done with this count, you must apply some unlock operation. What is this unlock? This unlock operation is releasing the lock. So this is the rule that we allow. So when you are done with your job of working on the critical section, please release the lock so that the other process which was waiting for this lock can get the lock and proceed, that is, enter the critical section. And this also, when this job is over, it should be releasing the lock so that other processes, maybe some process called PK, which was waiting for this lock, because it may also work on the critical section. So PK may have to get the lock, or maybe PI has requested a game, so PI will be getting the lock. So the rule is that in order to enter the critical section, you have to acquire the lock. So you do some operation so that you get the lock. And once you get the lock, you have a license to enter the critical section. That is to work with the shared data or data structure. So you work on that. When you are working on that, because you have got the lock, nobody else will be allowed to disturb you. Nobody else will be allowed to use that particular portion of the code in their part. Okay, so your updation is the one that is final. But when you are done with working on the critical section, as you are leaving out, please make sure that you release the lock so that others who were waiting on that particular lock can get the lock and can proceed. So this is the idea behind a lock and an unlock operation. Well, now that we have seen how synchronization can be implemented through use of lock and unlock pairs, which are meant to guard the critical section, the next question that comes up is, how do you implement this lock and unlock pair? Okay. So the answer to this is through multiple ways. So people have tried a number of ways to perform this lock and unlock. The first one is by using interrupts. So this is the most primitive way that people tried out in order to implement lock and unlock. The basic idea was that all operations in the operating system we know is implemented through interrupts, right? And that's one mechanism by which you can prevent certain operation and you can jump to any other operation. So suppose there's a process PI that would like to enter the critical section. So during the process when there is executing of the critical section, it does not want any other process to enter the critical section. And the easiest way to do it is prevent all mechanisms of any other process, or prevent all mechanisms by which any other process would have communicated to the OS. And the easiest way to do it is to disable interrupts of all other processes. Okay. So you disable the interrupts of the processor during the time when you are executing in the critical section. If you do that, then no other process can generate an information or signal to the operating system that I would also like to enter the critical section. So in a way, you are preventing all other processes from progressing. So the idea behind this is, if you would like to allow on process PI to enter critical section, so what you will do is, you will perform some operation called disable interrupt. Okay, and this is the lock that you perform. So if you disable interrupts, no other process now can put their request, because that will not reach to the particular processor. You have disabled. The only mechanism through which processors would be putting the request is through interrupts. If you have disabled, so nobody else will be. So you disable the interrupts before you enter the critical section, and when you are done with the critical section, you are sure that when you are working in the critical section, no other process would be able to send their request. But when you are done with this critical section, you have to ensure that you enable the interrupts. So this is the easiest way to prevent other processes from triggering or putting the request to the critical section. So this is the unlock that you are doing. Okay, disabling and enabling interrupts. Seems to be the most easiest way to perform lock. Okay. Yes, it is simple to implement because you are making use of already existing instructions. But the problem is that these instructions, which involve enable and disable of interrupts, these instructions are privileged, and if they are privileged, a user process cannot make use of these instructions. It has to request the kernel. So you go back to the same problem, because you do not have privileges to execute this in your code. Okay, this is the first problem with making use of interrupts. The second problem is that it's not suitable for multi-core. Processes PI, PJ, if they are operating on different processors, then disabling interrupts will not help, because when you disable interrupts, you are disabling interrupts of that particular processor. So a process that is making use of, if both processors are making use of the same processor, then it makes sense to disable interrupts, because the other process cannot make use of or cannot put the request to the CPU. But if the process is running on a different processor, so disabling interrupts of your processor has no effect on the process which is running on the other processor, because the process can then, the process running on the other processor will be able to put its request. So it doesn't make sense to use this. So this is the problem with interrupts being used to implement locking. Now, if interrupts cannot be used in the user process, people thought, can we perform some software-based techniques? Can we come up with some software-based techniques to perform this lock? So that is what we will be talking about next. That is the software-based solutions. Okay. And what we are going to do is, we will start up with a very naive approach, and then we'll gradually build on that to finally reach to the one that is most suitable. And in each case, whenever we try to come up with some software mechanism to implement lock and unlock, we will try to find out how good is our solution by comparing or trying to evaluate whether that particular solution has met our three requirements. What are these three requirements? Mutual exclusion, progress requirement, and boundary. So for every solution, we will try to find out whether it has met mutual exclusion, progress, and boundary. So these are the three requirements that we will be trying to evaluate. Let's begin our first attempt of utilizing a software-based solution to implement lock and unlock. So let's consider two processes, PI and PJ, and say both of them compete to enter the critical section. So how do you decide that which should enter the critical section? Let's start with a very naive approach, where we take a shared variable, say something called flag, and flag is initialized to either I or j. Okay, and let's impose a rule that depending on the value of flag, pi or pj will be able to enter critical section. So if the process ID matches to the value of the flag, then the process can acquire the lock or the flag and can enter critical section. So if flag is I, pi will get the value of pi will be able to acquire the lock. That is, pi will be able to enter critical section, and the value of flag is j, pj will be able to enter critical section. Okay. So what we will do, we will check whether the value of the flag matches to the particular process. So let us say if you are in process pi and pi has to check whether I will be able to acquire the lock. What will pi check? Pi will check whether the value of flag is not equal to or equal to j, right? So it will check whether the flag is equal to the value j, that is, the value is equal to the process ID, the other process. If it finds that this is true, what does it mean? It means that the flag is currently held by process pj. So I should wait, which means it has to wait. And this is the lock. So pi finds that this condition is true, that is flag is equal to j, and pi understands that the flag or the lock is currently held by pj. Okay. If flag is not equal to j, if flag is not equal to j, what will flag be? I. And if flag is I, pi understands that I will be able to acquire the lock. So pi gets the lock and it enters critical section. So that means if this condition is false, then you fall through this while loop and you get into the next line, which is you execute the critical section. Okay. So when you are done with this and you have completed the critical section, now it's time that you are coming out of the critical section. What should you do? You should turn the flag to j. Why? So that if you have made the flag equal to j, then pj may get this, because pj may have been waiting for the flag, and because flag value was I, that is the reason why pi had entered the critical section. So pj could not enter because it was waiting. And when will pj acquire that? Only when the flag has been changed to j. So it's the responsibility of the process pi to change it to the flag value to be equal to j. Let's look at this with a more easier approach. Let's consider two processes, say P1 and P2, and say the value of flag has been initialized to 1. Okay. So this is the shared variable, which in this case behaves as a lock. And what is P1 doing? P1, let's say, is, so what should we do in order that the P1 acquires the lock? So we will check whether the value of flag is equal to what? 2, right? So if value of flag is equal to 2, it means the flag or the lock is currently held by the process P2. So what will happen to P1? P1 will wait. Okay. But if this condition is false, that is flag is not equal to 2, that is flag equal to 1, then it falls through this while loop and it enters the critical section. Okay. But when you come out, you should ensure that the flag is made 2, so that anyone else who is waiting on the flag will be able to acquire the flag and proceed. So this is about P1. Let's look at what P2 will be doing. Same thing. Okay. So we will have a condition check which is equal to 1, and in case this is our critical section, and we will have flag equal to 1. Okay, so this is our lock section or entry section, whatever you call it, and this is the unlock or the exit section. So that is the one that we have for this as well. Okay, now that we have obtained this, let's try to argue whether this solution is a very simple one, right? We just introduced a shared variable called flag. We initialize flag can have two possible values, 1 or 2, and we decided that whatever be the value of flag, if that matches to the process ID, then that process will be able to acquire the lock or the flag and enter the critical section. And what we imposed is, in the critical section, we just check whether the value of the flag is equal to the value of the process ID. So it just checks whether the flag matches. In case you start off with flag equal to 1, let's say. So let's say flag was initially equal to 1, and suppose P1 is the one that is currently executing. P1 wants to enter critical section. So we come to the entry section or lock section, and let's see whether we have acquired the lock. While flag equal to 2, no, flag is not equal to 2, which means this while loop is false. If the while loop is false, you fall through this, because had this been 2, you would have got stuck here. So this is false, so you fall through this loop and you enter the critical section. That means P1 starts executing in the critical section, right? Now, when P1 is in the critical section, let's see, during this time, suppose there's a context switch. Okay? So P1 is in the critical section as a context switch. So P1, which was executing the critical section, now has been taken out, and P2 has started executing. P2 also wants to enter critical section, so it is also executing this part of the code. When P2 is executing this part of the code, it will also first execute this portion. It will enter the lock, and we'll find while flag equal to 1. Is flag equal to 1? Yes, because flag is equal to 1. Remember that this has not yet been executed. So P1 was executing. P1 executed till this. It had executed this. It had executed this, and there was a context switch. Now you came to P2, and P2 is now currently executing this line. So flag is still 1. Okay, flag is still 1. Because flag is still 1, this condition is true. If this condition is true, which means P2 will loop in this line. Okay, so as long as flag will remain 1, P2 cannot come out of this line. It will go on checking this and will loop. Again check and loop. So it will get stuck in this particular line. Okay, how long? As long as flag is equal to 1. So as long as flag remains 1, P2 will get stuck here. And if as long as P2 gets stuck here, P1, when it gets a chance, so P1 and P2, they are scheduled in this way. So P1, P2, P1, P2. So P1 executes these two lines, was currently executing the critical section, it was taken out. P2 started executing. P2 gets its chance, but comes in this line and gets stuck. It does not progress. So it never enters critical section. Again, P1 gets a chance. So P1 continues executing its critical section. Maybe it finishes the critical section. Even if it is not finished, no problem. Let's say again P2 gets a chance. P2 comes. But the first line that P2 executes is this and gets stuck. So it has to wait. This solution ensures that only one process will be able to enter the critical section depending on whichever of that gets or acquires the lock. Okay. And because the lock only has two possible values, and these two processes, depending on whether the value of that lock matches to their process ID, only one of them can enter. So mutual exclusion is guaranteed because you cannot have any other value, and both of them cannot, both the processes cannot have a value of flag same, whatever be the scheduling policy that you decide. They cannot have the same value of flag in process I and J or for 1 and 2. So mutual exclusion is guaranteed, okay, because you will have only one process executing the critical section at a point of time. Let's check out whether this solution meets the progress requirement. Recall, a progress requirement is one where a process, if it wants to enter critical section and there are no other processes in the critical section, the process should be immediately allowed to enter the critical section. That is, all processes which do not participate or do not wish to participate in critical section should not dictate others. Okay. Let's look at the condition. Suppose we start off with a situation where P1 wants to enter critical section and we have a flag equal to 1. So we enter, P1 enters this entry section, it checks out the value of flag, finds that the flag is not equal to 2, that means it falls to this, it enters critical section and makes flag equal to 2. So let's say P1 executed first, it went through its critical section, and while coming out in the unlock section it made flag equal to 2. Okay. So this is the condition declaration. Now after some time, P1 again wants to enter critical section. P1 again puts a request and P1 wants to enter CS. Now when it wants to enter CS, it enters this critical section, the entry section, and it checks whether flag is equal to 2. Yes, indeed flag is equal to 2 because it itself had made flag equal to 2. So this condition becomes true and gets stuck here. Okay, which means that it wants to enter critical section, but it gets stuck in the entry section itself. Why? Because it did not get the lock. But you may wonder why it didn't get the lock. P2 must have changed this to flag equal to 1. But say P2 does not want to enter critical section. P1 wants to enter critical section and P2 does not. If P2 does not want to enter critical section, then this particular piece of code will never be executed. Okay. If this particular piece of code, entry and exit section, will never be executed of P2, even if P2 gets scheduled, this portion will not be executed. If this portion will not be executed, then P2 will never make this flag equal to 1. And if P2 does not make this flag equal to 1, P1 will never come out of this, because P1 can only come out of this while loop when flag is equal to 1. But who will make this flag equal to 1? Flag equal to 1 can only be made by P2. But P2 is not going to execute this line because P2 does not want to enter critical section. Now you see the problem. P2 is a process that does not want to participate in the decision making of critical section entry, but it indirectly is taking that. So P2 indirectly participates by blocking P1, and this is what says should not happen. Okay, that means the progress of P1 is stalled by P2, a process that does not want to enter critical section. When we said that if a process wants to enter critical section and no other process, because P2 does not want, so it is not in the critical section. If it is not in the process, P1 should immediately be allowed, but this is not happening here. So that means, though this particular solution is good enough to ensure mutual exclusion, it does not perform the progress requirement, does not meet the progress requirement. So this solution does not work. Okay. Now let's take a second attempt in improving this. We found that utilizing a single flag was ensuring mutual exclusion, but somehow it was not able to satisfy the progress requirement. So an improvement on that would be, let's take two flags, okay, and let's call them as, say, P2 lock and P1 lock. And these two are two locks that we are going to use. So if P2 has to enter critical section, it has to acquire its lock, which is P2 lock. And if P1 has to enter critical section, it has to acquire P1 lock, right? And let's say these two locks are Boolean variables. So both of them are initialized to false. So if one lock doesn't satisfy, the obvious requirement is to go for two locks. And what we do is, if you are in process P1, then what we are going to check is whether P2 lock is equal to true. Okay. So this will tell us that if P2 has acquired its lock, that means I should wait. So P1 will know that if P2 has got the lock, P1 should wait. So that is why our entry section in this case will have a check of whether P2 has the lock. So when I am satisfied that okay, P2 has the lock, that means I am going to wait. So that is why we. But if P2 lock is not true, that means P2 does not have the lock. Okay, what does it mean? It means that now P2 does not have the lock, that means P2 is not in the critical section, so I can enter critical section. Okay, so if I can enter critical section, what I will do is, when I am working in the critical section, that is if P1 is working in the critical section, it should ensure that no other process should disturb that. So what will it do? It will make its own lock equal to true. Okay, it will make its own lock equal to true, so that the other process P2, while entering, will check the status of P1 lock. Pretty similar to how P1 checked the status of P2 lock, P2 will check the status of P1 lock before entering critical section. So when P1 is working in the critical section, and by making P1 lock equal to true, during this time, if P2 wants to enter critical section, it will get stuck here because it will find P1 lock equal to true. Let's look at it again. So we, instead of having two locks, in this case we are using, instead of having one lock, we are using two locks. And each of the process will check the status of the lock of the other process. If the other process lock is false, which means that it has the license to enter the critical section. So P1 will check the status of P2 lock, and P2 will check the status of P1 lock. That's the entry section of the respective process. Okay, if it finds that the other lock of the other process is false, it means that the other process is not in the critical section, so then that particular process can enter the critical section. So P1, if it finds P2 lock is not true, that means P1 can enter critical section. But before entering the critical section, it ensures that nobody else disturbs it by making its lock equal to true. So these two, they form the lock or the entry section. Similarly, when it is done, okay, it should ensure that its own lock is turned to false, so that any other process which was waiting on this particular lock should now progress. So this is the unlock or the exit or the release of the lock. Okay, why? Because maybe that process P2 was waiting on this, that is why it was getting stuck, because it was not getting P1 lock equal to false. Now that P1 has made P1 lock equal to false, now P2 will find this condition false and can move in the critical section. So this is how you can ensure that these two processes will be working with two locks. But does it really imply mutual exclusion? Seems to be, isn't it? Because two locks seems to be that okay, you are ensuring the locking. Let's look at a situation where we really perform mutual exclusion with this. Let's say you have the CPU that is currently executing this instruction, and we have the locks P1 lock and P2 lock. Remember that we initially started off with both of them false. Okay, and say so initially both of them were false to start off with, And suppose the first process that is executing, that is P1 is executing. So this is the condition that P1 is checking, that is P2 lock equal to true. So it is checking this condition. What will this condition result in? Because P2 underscore lock is initialized to false, and if P1 executes, it will find this condition to be false. If it finds this condition to be false, it means it enters the critical section. It has got a license to enter critical section, so it enters critical section, right? So this will find P1 underscore lock during this time is false. This is false. So this condition is satisfied, which means P1 it enters CS. Okay, this is what happens. Okay, but the problem is now you have a context switch. Okay, you have a context switch, and which means now your scheduler has taken P1 out and now has allowed P2 to get executed. So P2 starts executing. What will P2 execute? P2 also wants to enter critical section, and it will execute this line. So P2 will execute while P1 lock equal to true. This is the line it will try to execute. What was the initial value of P1 lock? It was false. So that means this condition will also be false. If it is false, it will fall through this line. And it will fall through this line, and what will happen is it will make this one equal to true. Okay, so this is still false, and what will it make? It will make, let's say, it will make P2 lock equal to true. Suppose it has gone through the next line, and it will make P2 lock equal to true. Okay. Now there is again a context switch, and you have the control back to P1. If the control is back to P1, remember P1 had already executed this line and had found it to be false, so it falls through this, and now it becomes P1 lock equal to true. So that means P1 lock, which was initially false, this was executed. Let me write it here. Suppose P2 lock equal to true, this fellow had executed this line, so it had made this to be equal to true, and now the control comes back to P1. P1 now executes this line, and what it makes is, it makes P1 lock equal to true, and that means it becomes true, and both of them, they enter the critical section at the same time. Okay, so both of them, P1 lock is also true, P2 lock is also true, and both of them now are in the critical section. That's what the problem was. That means this condition, or this solution, this attempt of introducing two locks, it fails the mutual exclusion property. So the second attempt also did not pay. Let's look at another attempt to implement the same locking mechanism. The only difference that we do is we just flip the two checks. Remember, in the second attempt where we were first trying to check whether the lock has been attained by the other process, and once we checked that it was not, then we entered, and before entering the critical section we changed the lock of that particular process. Okay, that was converted to or changed to true, and then the process entered the critical section. So let's flip that. Here now, instead of making the particular, so process P1, this line was in the previous attempt, it was coming after this check. We just flip these two lines and let's see if it works. Okay, so that means if process P1 wants to enter critical section, it will first make its own lock equal to true, and then we'll check the status of the lock of the other process. Okay, using this line. And if this turns out to be false, then it enters critical section. So that means I have ensured that my lock is true, and the lock of the other process is false, I check that, and only then I enter the critical section. So this is the lock section, you can say, or the entry section. Okay. And what do you do in the exit? So once you're done with the critical section, when you're out of the critical section, you just turn off your lock. That is, you make your lock equal to false. So this is the exit or the unlock section. Okay. And the same thing we do it for the other process. So in this attempt, we are again using the two locks, two Boolean variables, initialized to false, both of them. But the difference with the second attempt is, before we check the status of the lock of the other process, we make our lock equal to true. If you are in P1, we make the P1's lock equal to true and then check the status of the lock of P2. If you are in P2, you first make your lock equal to true, that's P2 lock, and then check the status of. The question is, does it satisfy all the three requirements? Mutual exclusion. Okay. So does it satisfy mutual exclusion? Yes, mutual exclusion. It really satisfies mutual exclusion, because the condition is, the previous problem that happened was that you were checking the other process, and then there was a possible context switch, and that led to the problem, because you read the status of both the flags, and in between there was a context switch, so both of them eventually came to the same value. But look at the condition here. Okay, so if you are using this P1 lock or P2 lock, okay, and if you have P1 lock equal to true and P2 lock equal to true, let's say if the condition was something like this, now the problem that could happen is, we may not guarantee, for mutual exclusion there's every possibility that mutual exclusion will be satisfied, because you are working with, you are first making your lock equal to true. So if the other person is having a false, then automatically the one that with the particular true lock will be able to enter. Now let's look at the other possibilities that can happen, and what we find is, if you look at this situation, so we have P1 lock, we have P2 lock. Remember, both of them have been initialized to false, and with this you would like to execute, say, this one. So what you do is, say P1 lock has been made true. Okay. P1 lock has been made true, so that means this becomes true, and now you are, suppose there's a context switch. There's a context switch and P2 lock also. So P2 starts executing. P2 also executes this line. P2 executes this line. And that means this becomes true. This becomes true. If P2 is allowed to progress, what will happen? So P2 has made this to be equal to 2. And what will happen? P1 lock equal to true. This is the condition that P2 will check. What will find? Because P1 lock has already been made true, so this will get stuck here. Okay? So P2 will keep on getting stuck here. Right? Okay, so P2 will get stuck here. Now, suppose there's a context switch. And the condition or the control is back to P1. So P1 will progress. P1 has already executed this line. What will happen to P1 here? P1 will check whether P2 lock equal to true. And will find P2 lock equal to true because we have just made P2 lock equal to true while in P2. So this condition will be true for P1 as well. So what is the situation? Because P1 lock and P2 lock both have become true, both processes P1 and P2 will get stuck, or will be doing nothing but will be executing this line, and every time they execute this line, they will get stuck here. Okay. So due to this condition, both P1 and P2 will always get stuck in this line. Why? When will P1 come out of that? Only when P2 underscore lock becomes false. But who will make P1 underscore lock false? It's the responsibility of P2, because you see this line is here. So until P2 underscore lock becomes false, P1 cannot come out of this line. But P1 will not be able to come out of this line because P2 cannot reach this line. Why? Because P2 will be getting stuck here. Why P2 will be getting stuck here? Because P2 will be executing this line. What is the line it is taking? Whether P1 underscore lock is true. Who will make P1 underscore lock equal to false? It is P1. So until P1 reaches here, P2 cannot progress. And until P2 reaches here, P1 cannot progress. So it's like a circular dependency. P1 needs P2 to progress and P2 needs P1 to progress. And this is a clear case of what we call deadlock. That means I depend on you, you depend on me, and nobody progresses. So you have no progress in this case. So this is another attempt which fails, okay, because it does not meet the progress requirement. We found that all the three attempts of solving this lock and unlock problem, it had some or other loopholes and it failed. Okay. Now let's try to have a fourth attempt, and this time we are improving on the previous three attempts. So the third attempt that we tried, we used two locks, okay, and the idea was that we'll first check, we'll first make, if you are a particular process, you will first make your lock equal to true, and then go on to check the lock of the other process, okay. But that had its own problem, that we found that there can be a situation where due to context switch, you may have a condition where both the locks will be equal to true, and then you will get stuck in this while loop forever, okay, without any progress. Now, an improvement would be that let's add a flag along with the two locks. So here we have three shared variables. All of them, they would be behaving or will help in creating the lock. What will be it? So apart from the two locks, we'll also have a flag, and the flag can have either value 1 or 2. Okay. So since the flag can only have two possible values, the process that meets that particular flag or the value of the flag, go back to the first attempt, it's pretty similar to that. It's like combining all the three attempts that we have done so far. So we have two locks and we have a flag as well. So the one that the process ID which matches to that of the flag value will be checking its own lock and then will be entering the critical section. So we'll have two checks to do. Okay. If you find that if either of them fails, only then you enter critical section. What do you check? You check whether the other person has the lock and the value of the flag is that of the other person. That is the other process. So if you are in process P1, you check whether your flag is equal to true. If it is not 2, that means it is 1. Or you have P2 underscore lock equal to true. That means the other person has the lock. The other process has the lock. Okay. So if you are in process P1, so the first thing you do is pretty similar to the third attempt. We make the lock of P1 equal to true first. So we ensure that that's a signal that I like to enter critical section. So you make the lock true. And now you are, you allow the other process to progress. And that is the reason why you change the value of flag to equal to 2, which is expected of process P2. So that's what you do. Okay. And then you make this check. So these three is what forms the lock section or the entry section. Okay. So the idea behind this is, this particular thing called flag is an addition to the third attempt, and the idea is that this particular flag will be able to break the time. So far we were using only these two, this was not there, and that led to a tie where you did not have this condition check, only this was the condition and that could time. So go back to the third attempt and see, in case there was one more thing that would be there and that could only take one of the two values, then possibly that would be breaking the tie, and that is exactly what is done by flag. So what this flag is doing is, it is able to break the tie in case both processes have their lock true. So this is the basic idea. And the one that is going to update that lock or update that flag will be losing the time. Okay? Because it is the one that is updating the value of flag. So if P1 is the one that is updating the flag, it is updating the flag so that it can allow P2 to progress. Because it is updating the flag with the value of 2, that what P2 needs. So the one who's actually updating the flag last will be losing the time. Okay? So the process that updates the flag last loses the time. Let's see. So suppose with this initial condition, you start off, and if you are process P1, P1 will be making itself true, so this will change to true, okay, and it makes flag equal to 2. Now there's a condition to be checked, whether P2 underscore doc equal to true, P2 underscore doc is not true, so that means it's false, and if any one of these conditions is false, you fall through this loop, okay, and then you enter the critical section and execute, right? So now, whatever be the case and whatever be the situation in which context switch happens, we have a flag associated with others. So we are performing 2 condition checks, and that along with an additional flag ensures that we can only have one possible value of the flag in either of P1 or P2. So that ensures mutual exclusion, because you cannot have any other value of flag. Okay, so that means there can never be a situation when both processes will have the same value of flag, because a process updates the value of flag with a value required by the other process. So since you are making a condition check with the flag as well, this ensures that there will be mutual exclusion. And there is also a possibility of tie that was there had this flag not been there. So this possibility of a tie which was there in third attempt is again removed by applying this flag, okay, which is the one that touches this flag last is going to break the tie. So there is no possibility, even if there is a tie, an additional flag ensures that it is broken. So you also go through this progress requirement. Okay. Now finally we have something called the bounded weight that needs to be checked. And what does it say? If a particular process wants to repeatedly go into the critical section, you have to put an upper bound. So it's not that it should not allow other processes to starve. And that's applicable here because we are switching alternatively between process P1 and P2 because of this flag and this one. So there is no chance that a particular process will keep on, if either of these two processes will keep on executing the critical section, because at some point of time they will be changing the value of flag, and that will reflect in the other process, and the other process now will get a chance to move ahead. So by using this, you are also preventing or you are ensuring the boundary. So this solution seems to be the best of all, because what we did is we gradually started out with a very naive approach of a single flag, then we used 2 locks, we flipped their position, and then we understood that even that is not going to help. Then we combined all the 3. Third attempt was very near, except that we ended up into a deadlock situation. Then what we did is we introduced 3 locks or 3 shared variables, and we used all the 3 to check whether some process would be allowed to enter the critical section, and we found that this is the best of all. And this is what we know as the Peterson's solution. So this is the best software solution that we have to introduce the locking mechanism in order to ensure synchronization of processes.